Module 9 phase diagrams, part 2, the lever rule. Let's look at a part of the copper-nickel phase diagram that we were studying in the previous part. We understood that we could see which two phases were in equilibrium at a given temperature. So if we call that temperature T1, if we know the average composition of the alloy, if the intersection of the average composition, which is C sub 0, and the temperature lies within a phase field that contains two phases, then yes, we have two phases in equilibrium. We can find the composition of those phases by seeing the intersection of the phase boundaries either side of the point B here. So we draw a horizontal line representing that all of these points represent points with the same temperature. Now the intersection of this line, the tie line, when extended to the left, we intersect that with the first phase boundary, which we see here as a phase boundary between the liquid and the alpha in liquid. So this will give us the composition of the liquid, C sub L. Similarly, as we extend the tie line to the right from point B, and we hit the next phase boundary, which is the phase boundary between alpha and liquid and alpha, therefore it represents the composition of alpha. So we have the compositions, but perhaps we want to find out what the mass fractions are of each phase. In order to do that, we will use the lever rule. Let's do a derivation of the lever rule. Here we have a section of a hypothetical phase diagram where we have a phase field that contains two phases in equilibrium. Now let's say that the combination of the temperature and the average composition, C sub 0, lies within that phase field with two phases in it. I've called them P1 and P2, representing phase 1 and phase 2. This phase diagram is for a two-component system containing component A and component B. The horizontal X scale represents the weight percent of B. So let W1 equal the mass fraction of phase 1 with a composition of C1, weight percent B. And let W2 equal the mass fraction of phase 2 with composition C2, weight percent B. So the mass fraction is the mass of a certain phase divided by the total mass of the system. Let's consider 1 kilogram of total mass of average composition should be C0. In such case, if we have, let's say the average composition, C0, let's just say that's 50% B. 50% is 0.5, so as a fraction, if we multiply 0.5 by 1, we get 0.5 kg. So we expect if C sub 0 were 0.5, or in other words 50%, we expect there to be half a kilogram of component B within the system. So we can express the total mass of B as the mass fraction of phase 1 multiplied by its composition expressed as its fractional composition of B. Adding to that the mass fraction of phase 2 times the composition in terms of its fractional composition of component B. If we add these together, we should get the average composition, C sub 0. As there are only two phases, the fractions, W1, W2 must equal 1. We can rearrange this to get W2 is 1 minus W sub 1 and eliminate W2 from this equation. In such case, we get the product of W1 and C sub 1 is equal to 1 minus W sub 1 C2, which equals C0, distributing the C2, like so, and collecting our terms, we see that W1, C1 minus C2, equals C sub 0 minus C sub 2. We can rearrange this and see that the mass fraction of phase 1 is equal to C sub 0 minus C sub 2 over C sub 1 minus C sub 2. These are going to be negative numbers because C2 is larger than C0 in our diagram, but we can just multiply top and bottom by minus 1 and get this equation. C2 minus C0, let's have a look on the diagram what that represents. C2 minus C0 is this length expressed as the difference of weight percent B. And we're dividing that by C2 minus C1, which is the total length of the tie line expressed as a difference in composition of C2 and C1. So this is called the lever rule, where the weight fraction of phase 1 is going to equal this length B divided by the total length of the tie line. Similarly, the mass fraction of C2 is going to equal this length of the tie line A divided by the total length of the tie line. Okay, that's just an easier way to remember it rather than looking at this equation. So in this way we can get the mass fractions of each phase. This is expressed as a fraction, and we can multiply by 100 to get percent. We could even use A and B in percent values, and they will cancel out and give us a fraction, a mass fraction for each phase. The lever rule will only work in phase fields where you do have two phases, okay? And you must have, as you can see from the derivation, we've assumed that there's only two phases possible, and hence the sum of those two mass fractions that we calculate will equal 1 or 100%. So we can see we can certainly apply the phase rule in this phase field, and this phase field, in this one, in this one, in this one, which will be which will contain gamma and Al3Mg2. Now we cannot apply the lever rule in single phase regions, so we can't apply it there. We can't apply it there because it doesn't make sense, because there's only one phase in those phase fields. Okay. Let's have a look at the application of the phase rule to a typical textbook problem. So it says here a 65 weight percent nickel, 35 weight percent copper alloy is heated to a temperature within the alpha and liquid phase region. So let's just put this is 70, so 65 will be here, like so. So we're somewhere in this region here, and we're between the liquidus and the solidus. It says here if the composition of the alpha phase is 70 weight percent nickel. So where is 70 weight percent nickel? Right here. So let me draw another line. I'll draw that in green. Oh, wrong color. Let me just change that. This is 70%. There we go. So this is the 70 weight percent nickel composition. So we're somewhere along here. So the only place that occurs is at that point here on the solidus. And so what we want to do, we can read off the temperature by drawing a horizontal line, and I'll choose blue for that. Let's draw a horizontal line right here, and we can roughly see the temperature here. If we want to get a more accurate measurements, what I recommend you do is we can copy this image. Oh, you can actually, in my software, you can actually save it as an image, and this will just speed it up. But in other ones, you can just copy and paste it into Paint. Okay, so I'm just going to call that example problem 1. And then I can use a online way to convert points on the graph into numbers, and I'm using here graphreader.com. So I'm just going to change the focus of this so you can see what I'm looking at here. So graphreader.com. I'm going to now select my file. Just right here. And go. And there it is. So I'm just going to zoom in there. You'll see as I move my cursor, you'll see the X and Y. But we need to calibrate those points. So I'm going to drag this blue box to that point. And then here I'm going to set. So my Y high, the high value for the Y is 1600. The low value for Y is 1000. The low value for X is 0, and the high value is 100. Press enter. Let's just check if it works before we trust the values. So over here we should get X is 0 and Y is 1000, and that's close enough. Yeah, that's good. And over here we should get X is 100 and the temperature is 1600, so that works. So now I can quite accurately read off this temperature. The temperature there is 1343, so I'm quite happy with that result. So for A, we see the answer is 1343 degrees centigrade. Now it's asking for the composition of the liquid phase. Well, there's two phases in equilibrium. We can draw the tie line for this average composition and temperature, and the tie line will extend until it hits the next phase boundary, which is right here, which is the liquidus, and the composition of the liquid will be given where the vertical that we drop from there intersects with the x-axis right there. So we're expecting a number about 55, but we can get more accurate reading by using this online tool. So this point here, it's actually, I'm getting 50, I'm getting 58, okay. And this would be 58 weight percent nickel. C, we want to calculate the mass fractions of both phases. So W for the liquid, the mass fraction of the liquid will be the length of the tie line on the bottom. So the length of the tie line would be 70% minus 58. And if we want to know the mass fraction of the liquid, we need to find the tie line that goes between this intersection point here and the where the tie line intersects the other the other phase boundary, so to speak. So if this is length A over here, and this is length B, then in this case, because we want the mass fraction of liquid, we actually want to put the number B on top, okay, the length B. B is simply going to equal 70% minus the average composition there, which is 65. So when we calculate this out, we will get the mass fraction. (70 minus 65 over 70 minus 58, which is 0.42, which is the same as 42%. So that's the mass fraction. Now, the mass fraction of the other phase, which is alpha, is going to equal 100% minus 42. Or we can reapply the equation. This would be the length A divided by the total length of the tie line, which goes from 70 down to 58. The length of A is going to be, in this case, that's going to be the average composition here, 65 minus 58 over 70 minus 58. (65 minus 58 over 70 minus 58), and that is 58.058, which is the same as 58%. As you can see, if we add these two numbers together, we get 100%. So I hope that helps.